Hello and welcome. Today we're going to be deriving the wave equation. And this equation, this is going to be a new PDE that we're going to study. And it's all about modeling mechanical vibrations. All right, so our old PDEs so far, as we conceive them, are all based on conservation. They're all based on conservation, right? So with the heat equation, of course, we had thermal energy, right? And for the diffusion equation, what we had was mass conservation, right? So the question is, if we're going to be modeling vibrations, the question we have is, what is the conserved quantity? Well, let's stop and take a little bit of a step back here. So when we talk about modeling mechanical vibrations, we're talking about vibrations in a material with spatial extent. If you have material with spatial extent, then so again, we're gonna really focus on one-dimensional equations for now. So just x in space. All right, and if we're going to talk about motion, of course, is a vibration, or vibration is a motion. So what involving with motion is conserved? It turns out there is something that's conserved with motion, and it's going to be what they call momentum. All right, momentum is a conserved quantity. All right, so let's review momentum a little bit. So again, we can think of a system. The typical system is that of two billiard balls. If we have two billiard balls, maybe one here, mass 1, and it has a velocity 1, and then we have mass 2 over here, and it has velocity 2. All right, and they're headed for each other. We know that the system momentum is going to have to equal a constant at all times, and it's going to be m1 v1 plus m2 v2. All right, so later on, at some later time, if we check up on our system, there was probably a collision where the two balls collided, and perhaps then now you have m2 going this other direction. It's going to have a new velocity, which we'll call w2, and m1 will have a new velocity called w1. So this, because it's constant at all times momentum, essentially m1 times w1 plus m2 times w2, that has to be equal to the velocity before the collision. All right, so this is good when you have a system of just two masses and you have some sort of elastic collision. The question is, how do we find, approach momentum conservation in a material with spatial extent? So again, we're thinking in 1D, and we're going to think of a material as basically a string. And what we're going to do is we're going to segment our string into little pieces. Each piece will be like a little delta x. And basically we can think of this as having a mass here and a mass 2, a mass 3, and so on and so forth. And then we can ask ourselves, if there's motion in this object, let's say that there's some velocity 1, and there's some velocity 2, a velocity 3, and then a velocity 4, and so on and so forth. Like that. Right? So the next question we have, of course, is that what we want to know is, if we have a material and each of these masses is having its own momentum, there has to be some way for momentum to exchange between neighbors. Okay, and we can imagine this sort of thing happening and producing waves. We can imagine that there's some sort of wave that's traveling down this medium like that, and that's basically, anytime you've played with a string or watched vibrations or stomped on the ground, you can see a vibration travel through the medium that you're impacting, and that can create a wave where essentially momentum in one region is somehow transferred through the elasticity of the medium itself to other regions, and there's some sort of propagation. All right, so let's see if we can figure out how to formalize this. All right, so how do we model wave propagation? All right, so again, what we're really trying to do is actually do what's the actual math of this? Well, the answer to that question is we're going to have to develop a free body diagram to describe basically the effects or the forces on each segment of the material. So what is our specific material? We're really going to be identifying that of an elastic string. So an elastic string, I like to think of this, the best way is think of it as a guitar string. A guitar string, of course, that is under tension. It's under tension. And clearly, of course, it can vibrate. That's very important. So really, that's what we have to have in our mind all the time, is think of a guitar string or some stringed instrument. And we want to know essentially how the string moves through time. And of course, different segments of the string will vibrate at different frequencies, or could vibrate in complicated ways, each segment being affected by its neighboring segments and so on. So it's under tension. And let's see if we can let's just get some notation here. First off, here's our string. We're going to segment it out like this. And each segment will be a delta x. All right. And what we're going to talk about now is rho. There's going to be some mass density to the string. This is going to be, of course, our segment length. And we know that calculus is, of course, part of partial differential equations. We're going to do all our analysis on a segment, and then we're going to take delta x smaller and smaller and smaller in order to get a differential notation for all of this. Okay. Second, we have to define our axis here. So u of x comma t is going to be the vertical position of our string, like that. All right, and we have to come up with a few other things. And we assume at the endpoints that the string is anchored. All right, so the string's not flying off. It's not. It's anchored and it's under tension. Again, we're thinking about a guitar string. These are very standard things to imagine when considering a guitar string strung across a guitar and under tension. Okay. All right, so these are all the pieces. Let's actually come up with a free body diagram. So U is our vertical position, and then we have A, and then we have B. And we could represent this as follows. There's our string. Actually, let me draw that a little bit better. Like that. I'll bring that point a little bit further in. Right there. So here's our segment. It goes from A to B, and that's going to be delta x, so that's going to be B minus A right there. And the mass of this string, of this segment of string, is going to be rho times delta x. Okay, cool. So the motion of the string, that's going to, of course, be determined by forces. All right, so we know that F is equal to ma. Well, we know m already. A, of course, is acceleration. That's going to be utt of our string. Okay, so that's good. But now what is F? Well, F is going to, of course, be the net force on endpoints. So we're not going to think about any internal forces. We'll assume all of those are neutral. But rather think about the forces on the endpoints. So, of course, we have two. We have two endpoints that we have to worry about. Okay, and these forces are going to be tensions. That's how we'll describe them. So there's going to be a TB there, a vector that way. And also, of course, a TA there. They can be described by an angle, theta A, and an angle here, theta B, like that. Okay, so now we have all those pieces put in place. And now what we want to talk about now is, so of course, we have to make some assumptions now. Okay, so the idea here is, of course, that m times utt is going to be equal to TA plus TB. Something like that. But we have to fill in what exactly that means. So we're going to have to come up with a list of assumptions here. Okay, and again, these are going to be applied to a guitar type string. Okay, so these are assumptions that would be a sensible thing to assume or to assert in a situation of a guitar type string, some sort of suspended cable under suspension. All right, so the first assumption, and these are going to start off real slow, and each assumption that we're going to develop is going to kind of create new assertions that we can make. So we're going to talk about small angles. We're going to assume theta is small. Okay, so theta is small. That is a really good assumption to make. And that, of course, is appropriate. Again, imagine a guitar string. If you pluck a guitar string, of course it's going to move up and down. There will be angle deflections on each segment of screen, but they're going to be really small. That is, that theta is going to be near zero, right? It's just going to be small deviations from zero. It's not going to be big ones. And that is a sensible thing, provided that string is under enough tension. Okay, 2. We're going to talk about the cosangle small angle approximation, which is 1. So this is called a small angle approximation. So a lot of students, I think, are more familiar with the sine angle approximation. This one is maybe a little less familiar, but it's a very important one. We're going to be using that one quite a lot. 3. Okay, so this one is a really important one. There's no horizontal motion of the segment. Okay, and of course this is also sensible. It's a sensible assumption. Again, look at a guitar string. If you watch a segment of string, it's more or less going to be only vertical motion. There is no side-to-side motion to speak of, and that's because the string is under tension, and at the end points there is equal and opposite tension on every segment. So what we can actually say there is equal and opposite tension on every segment. All right. What's the next assumption we want to assert? Well, before we get to that, let's talk about what this means. So of course, if we have T, our vector of tension, I can write it as the magnitude of that tension times a vector cosine theta sine theta. Right, I'll write it as a column vector that I'll just transpose over. All right, well, so if I say there's no horizontal tension, so we can actually put these on here now. We'll talk about two. So I'm gonna put on our graph here on our free body diagram. There's a TH and a TV, right? And the same one, there's one over here. There's the TH. Of course, those THs will be the same. They'll cancel each other, and they're the same magnitude. And we have a TV down there. All right. So what we mean here is that TH has to be equal to the magnitude of T times cosine of theta. But note here that go back to our assumption I. We know what that is. That means that that's going to be equal to just the magnitude, or it's approximately equal to just the magnitude of the vector itself. So that means the total magnitude is pretty much all composed of horizontal tension. All right, that's a really good assertion to make. Okay, so now let's talk about this fourth assumption that we want to make. What we're going to now talk about is TV. I want to talk about TV. I want to figure out what we can say here about that. So we know that that's going to be equal to TH times sine of theta. But what I can do here is now divide by cosine. Like that, right? Of course, that gets us TV, that gets us a tangent of theta. But we also notice that that is basically that's going to be TH times the rise over the run, which is equal to TH times, effectively, the derivative of U with respect to X. So our vertical tension, and this is probably the most important one, our vertical tension, the component that's going to drive motion vertically in the string, is related to the spatial derivative. So that's a really important assumption. Okay, so for the so we can think of this as actually the fifth assumption, is we can make this assertion that rise over run is equal to the derivative. Here we're making that small, in IV we're making the tangent approximation to the vertical component. Sorry, I kind of overdid that one. So finally, VI, the sixth assumption, and this one is a pretty simple one. There's no resistance in the string to bending. So what we can really say here is is not a beam. So we're not modeling a beam, okay? So in fact, there is a PDE called the beam equation. So this is, of course, we're going to have to see a future video. And let's think about what it means there's no resistance to bending. So, of course, if you've ever examined a string, there's always some resistance to bending, a cable or something like that. But we have to think about it in this way. So the resistance to bending, think of it as negligible. It's negligible compared to TH, that horizontal tension that the string is under. And again, imagine a guitar. If you push your finger against a guitar string, clearly there's going to be a force that's counteracting your pushing. Most of that force is transmitted through that horizontal tension. It's due to the tension that it's undergoing as being suspended across the bridge and the nut of the guitar fretboard. What very little of that resistance is going to be due to bending forces. Beams, on the other hand, they are designed to resist bending. In fact, that's their primary job, you can think of, is to resist bending. So there are other equations that model that type of situation, but this particular model does not have that force in it. There is no bending force. Okay, so now let's see if we can put all this together. We've got a lot of good pieces here. Okay, so what we have, MA is equal to rho times delta x. That's my M there, times UTT, and that's going to be equal to the sum of all the forces, which is TA plus TB. But now we're going to actually call them the vertical forces, because again, there's no horizontal forces. There's no horizontal force that don't cancel. So there are, of course, horizontal forces that each segment of string, at each end, those horizontal forces are equal and opposite. So that's what's really important here. All right, so, and now we know that, let's draw our free body diagram again. A and B, we have that tension TA, we have that tension TB, and we now know that there's a TVA there and a TVB there, and those 2 points there are going to determine the net of those two forces are going to determine what's happening to this thing. So we know that TAV, let's figure this one out. It has a force that's going to be equal to TH times the derivative with respect to x. However, note that there is, look at the slope here. If I look at the slope, we know that we have to put a negative sign on this one right there, right? Because positive slopes on the left-hand side yield downward forces, right? So we're gonna have to negate that thing there, right? Likewise, if I go to the other side, TBV, we're gonna get a positive force, TH, times the derivative. All right, and that's just because we have some boundary. We have a boundary or an orientation convention that we have to adhere to. That basically, because it's on the left side, we negate it. On the right side, we don't. All right, so we're going to evaluate that at a comma t, and this at b comma t. All right, so we've derived that from before, so let's put this together. So this is going to be at x comma t, and it should be noted here that we're just picking some point, call it x. It's some sort of representative point in a comma b. Okay, great. And that's going to be equal to negative th partial derivative of u with respect to x, a comma t, minus, or positive plus th partial derivative of u with respect to x, b comma t. All right, so what I can do now is divide this whole thing by rho delta x. And then, of course, we get utt is equal to th over rho. We'll put that parameter out front. And then after we move everything around, we're going to get ux at b comma t minus ux at a comma t all over delta x. Of course, if I take delta x goes to 0 here, what we're going to get is a u double derivative right there. So that, of course, is our major calculus thing that we're going to do. So we end up with this differential equation, our partial differential equation. So there we have it. So it might be important for us, though, to also just note that basically we're looking right at a flux law. So basically momentum transfer is going to be equal to phi is negative th partial derivative of u with respect to x. So this is our flux law. That's how momentum is transferred, is due to the negative gradient of the string's basically its slope. All right. It should also be noted that we can also apply other forces, which we'll call f of x, to the string. All right, so in this case, what we want to do is put that on top here. So I'm going to call that 1, 2. The next thing we can do is we're going to define th over rho to be a special parameter called c squared, where c is going to be called the wave speed, or wave velocity. Let's figure out what that wave velocity is. Figure out the units. So th, that's a force. And rho, that's of course a density. Put them together, th over rho. What we have here, of course, is kilograms. We have kilograms times meters per second squared, all over kilograms per meter. If I put those all together, of course, the kilograms cancel, and the meter in the denominator there flips up to the numerator, and you get c squared is equal to, has units of meters squared per second squared, which is, of course, velocity quantity squared. So that's why we call this the wave velocity. It should also be noted that this parameter, you can think of it, now try to figure it out here. C squared is equal to th over rho. So if I make th big, Okay, that's sort of basically tightening the string. What happens to a guitar string that you've tightened the tension on it? It's going to give you a higher note, a higher frequency vibration. So the wave velocity could also be called a vibration. It relates to the vibration frequency. All right, also, think about taking rho, make that big. Think about a guitar string. You know that there's many guitar strings. Of course, that should slow C down a little bit, right? So rho being a more dense string. So think of the lower notes on the guitar. Okay, you're going to have lower frequencies. So what we have here, of course, is C, the actual wave frequency is going to be the square root of TH over rho. So there you go. All right. So now that we have these two things here, we have both the applied force that we're going to add and this new definition for a parameter. Our wave equation is going to be the second time derivative of u equals c squared, the second space derivative of u, plus an applied force, f of x, like that. All right, we can have boundary conditions too. Typically for a guitar string, that would be what we call a fixed end. So the idea here is, of course, that you're going to anchor the strings at some points 0 up to L, so that u of 0, comma t, is equal to u at L, comma t, is equal to 0, right? You could also have what's called a free end. And this is a little bit stranger, but this is where you set the derivative at the endpoints equal to 0. You still have to keep them a fixed distance apart, but what you've allowed them is to basically move on tracks so that there's never any slope at the endpoints, so that your string can slide up and down. They're not fixed at any specific anchor. So those are the boundary conditions for the wave equation. We're going to leave it at this. We have a new PDE. This is our new PDE to study, and we can use separation of variables. To solve. But we're going to do that in the next video, where we'll actually explore the solutions to this. So thank you very much, and I'll see you in the next video.